Hello students, this is Mr. Allen, and today we are going to look at section 8.9, which is on representation of functions by power series. So last week when we met, we looked at power series, and today we're going to actually try to use power series to represent a function. So that's our main objective. And then our second objective here is to construct a power series using operations, which I'm going to do examples of both. So consider the function f of x equals 1 over 1 minus x. This is very similar to our geometric series, if you recall. Remember, a over 1 minus r, which gives us this geometric series, and this right here is our radius of convergence. As long as we're within 1 away from our center, which is probably 0 in this case, then we're good. In other words, in our example above, a is 1 and r is negative x. Oh, not negative x, it's positive x, sorry. Positive x here because this is a minus and that's what we wanted, so it's going to be positive x. In other words, our power series representation for 1 over 1 minus x is simply the sum from n equals 0 to infinity of x to the n. And that's when it's centered at 0. Of course, the series f of x is only represented when we're on the interval from negative 1 to 1. So on the left, we actually have the function. On the left here, we have our function 1 over 1 minus x, and its domain is all real numbers except for x equals 1. But our power series is only valid on the domain of negative 1 to 1 because that is what our interval of convergence is. So we have a restricted domain, and if we want to represent f in other intervals, we have to develop a different series. So the series we developed on this previous slide is only for when we have it centered at 0. For instance, let's say we wanted to have it centered at negative 1. Well, then we could rewrite it. Remember, we're starting with 1 over 1 minus x. So if we want it to be centered at negative 1, that means we got to move it to the left 1. So that means we got to substitute x plus 1 in for x. So that gives us the following. Oh, one other important note here. If I put x plus 1 here, I have to account for that on the left-hand side. So this was 1 minus x. So what I've got to do, if I put x plus 1 there, is I now have to change this 1 to a 2 because I'm minusing that 1. Let me say that again. These two fractions are equivalent. On the bottom, I have essentially added 1 to the x, so that means I have to basically add 1 to that 2. In fact, if you want, just simplify it, and you'll see what's 2 minus the quantity x plus 1. It's 1 minus x. You can check that. Now, I've got one more step, though. Remember, we want it to be of the form 1 over 1 minus r. I'm sorry, a over 1 minus r. So we don't want this 2 to be here. So that means we have to divide through by 2. And so that gives us what we need here. Let me go ahead and erase everything I've got on this slide. So hopefully this makes sense. So again, let me go back to the beginning. If I want this centered at negative 1, I have to, if you will, massage my fraction to look like it's in the correct form still, but now we've got x plus 1 in for x. This now means that a is 1/2, and r is going to be this quantity x plus 1 divided by 2. So for the absolute value of x plus 1, which is less than 2, we have the following. 1 over 1 minus x is equal to the sum of 1/2. That's your a value. This first value here, that's your a. Here's our r value to the end. So that is the power series representation for the exact same function, but this time it's centered at negative 1. And here is the expanded notation. Notice now our interval of convergence is from negative 2 to 1. And that has something to do with the fact is that we're now shifted over to the left one, and we've got this factor of 1/2. So it's actually, we've got a little bit more interval to deal with. So let's look at our first example. So here's this question that you might have on the homework. It says, find the power series for f of x equals 4 over x plus 2. This one's going to be centered at 0. So remember, our goal is to write our function in the form of a over 1 minus r. So we can do that. So the first thing we want to do is we want to take the 2 and the x and switch those around. We don't want that 2 there in the denominator, so we got to divide through by 2. So 4 divided by 2, that gives us the 2 in the numerator, and the 2 divided by 2, of course, is just 1. And then we've got to remember, we want this to be minus r, so we had to do the minus x over 2. So now this is in the form that we want. We have a is 2, we have r is negative x over 2. Again, I want to emphasize this is the form we want to get it in. Therefore, our power series for 4 over x plus 2 is simply going to be the sum from n equals 0 to infinity of 2, because remember a was 2 on the last slide, and r here was negative x over 2. So it's that easy. You just plug it into this formula and you've got your answer. Here's our f of x. That is the power series. We can write it in expanded form, which would look like this by just starting with 0 and plugging in values for n. And we also need to make sure that we have our r value being less than 1, the absolute value. So our interval of convergence here, once you solve this inequality, it's centered at 0, and we can go from -2 to 2, excluding the endpoints. That's our interval of convergence. So that's our first example. All right, here are some operations for power series. So if I have a power series for f that's represented here, and if I have a different power series representation for a different function g, so our first rule says if I take a constant k times x inside of the function, then all you got to do is plug k to the end inside there. If I take my x to some power, which we're going to see an example of that here in a minute, then you just got to take that x to the n and multiply it by n. By the way, n, capital N, this is going to be some integer. Typically, those are greater than 0, at least in most cases, yeah. And then the last property here, or operation, is if I have two functions and I'm adding and subtracting them together, I can simply add or subtract them within the power series themselves. So let's see an example of that. Example 2, adding two power series. So I've got my function f of x, and I want to find a power series for it, and we want to make this one centered again at 0. Obviously, centering them at 0 makes these a little bit easier to do. So now we go back to chapter 7, and we think about how we use partial fractions. So it turns out that this fraction is equivalent to the sum of these two fractions using partial fraction decomposition. 2 over x plus 1 plus 1 over x minus 1. Now what we can do is we can deal with both parts of this separately, and then we will add our results at the end. So our first fraction, which was this 2 over x plus 1, we can play the same game we just played. We're going to leave the 2 where it is. We're going to switch the 1 and the x and then make it minus x. So we're going to get our power series here from sum from 0 to infinity of 2 times negative 1 to the n, x to the n. The second power series, the second function, we do the same thing. We've actually already kind of seen this one. The only thing we need to be careful of here is when we switch the x and the minus 1, we got to deal with a negative here. Okay, because we got to switch the sign on that x to make it negative. So we need to be careful to do that. Now, here's the beautiful thing. We can go back and we can use this third rule. So basically what I'm doing is I'm going to take this power series and this power series, and I am adding them together. And so that's what we do. So you'll look at this 2 times the quantity negative 1 to the n, x to the n, and this x to the n. Don't forget the minus. And hopefully you can see where all of that comes into play. So here's our power series for that particular function f. In expanded notation, it would look like this. And our interval of convergence actually does not change. Just like the original 2 had interval of convergence, radius of convergence of 1, so does their sum. All right, last example. Finding the power series for g of x equals arctan of x centered at 0. Now this is the most interesting example, so stick with me here. Again, we're talking about using these geometric power series to write functions. So what we have here is we're trying to find the power series for arctan of x. Now I'm going to draw back on something that we learned back in, I think, chapter 2, which was differentiation. So this is Calc 1. The derivative of arctan is 1 over 1 plus x squared. Again, that probably doesn't mean much to you, but just pay attention here. Let's see what we can do with that. Well, we know that if f of x was 1 over 1 plus x, then that is equivalent to the power series negative 1 to the n, x to the n. Actually, we just saw that on the last example. Furthermore, I'm not dealing with just an x in the denominator. Remember, in this problem, I have this x squared. So I can use those properties now, and instead of plugging in x, I'll just plug in an x squared, and then there we go. So by that goes back to that second property a few slides back. So hopefully if you compare this power series to this power series, the only thing that changed is that 2 in the exponent for x. So what I'm telling you is that the function 1 over 1 plus x squared is equal to that power series, which was, again, the derivative of arctan. So let's pick up where we left off with that. If I don't want the derivative of arctan, I want arctan by itself. So I need to undo differentiation. And how am I going to do that? By integration. So if I integrate both sides by the fundamental theorem of calculus, arctan is simply going to be the integral of this. And oh, by the way, don't forget that plus c. Well, we just saw on that last slide that 1 over 1 plus x squared was equivalent. In fact, let me write that right here. This was equivalent to the summation of negative 1 to the n times x to the 2n, period. This was this sum right here. This sum was the geometric power series for 1 over 1 plus x squared. Now we're integrating, and then we're going to use the power rule for integration, which tells us what do we got to do? We need to add 1 to this exponent, and then you've got to divide by the new exponent. So hopefully you can appreciate where that came from. Now, let me not go too quickly through this and make sure you appreciate what just happened. We just integrated a power series. I just used an integration rule for a power series. So I went from the power series on this last slide here at the bottom, and I have essentially integrated it here to get this power series right here. And by the way, don't forget, I still have that plus c. But the good news is we said it was centered at 0, so guess what c is? A 0. Therefore, arc sine, the power series for arc sine centered at 0 is the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1. So if we start with 0, when you plug 0, this is going to just generate the odd powers. This is actually not quite correct. Get rid of, I am sorry, this is a mistake. Get rid of, let me do this in red here. These leading numbers here, I've got to fix this in my notes. I was going to take them off and I did. There should not be a 3 and a 5 and a 7 here in the numerator. These are only in the denominator. So the first one, when you plug in 0, you're going to get positive 1. Then you're going to get x to the 1. So that's why it's x to the 1 over, well, 1. When you plug in the next number, which is 2, when you plug in 2, you're going to get positive. I'm sorry, when you plug in 1, the first number you plugged in was 0. The next number you plug in is 1. When you plug in 1, you're going to get negative. That's where this negative comes from. And then you're going to get x to the, well, 2 plus 1, which is 3. There's no, that 3 should not be in the front there. I will fix that in the notes. So the answer is, in fact, let me just go ahead and write this correctly. It should be x minus x to the third over 3 plus x to the fifth over 5 minus x to the 7th over 7, etc. And the interval convergence on this one is negative 1 to 1. So that will be that. Thank you so much for your attention.